Okay, so let us start the session. So good morning, one and all present here. Morning to Mr. Amulya Ratna. So let me introduce Amulya sir, then we'll start the session. Am I audible to all? Amulya
Yes,
sir?
sir. Good morning,
Okay,
sir.
fine. So Amulya Ratna is an AI and NLP professional, currently serving as Associate Director AI at IQVIA Bangalore, India. He holds an MTech degree from BITS Pilani and is also currently pursuing his PhD at BITS Pilani. So his research interests include raw research, natural language processing, deep learning, generative AI, large language models, multilingual language technology, and mainly machine translation. So he has done many works on Odia machine translation and in other languages also, like European language also, because his company is working on that. So he's particularly interested in developing AI solutions and underrepresented and low resource languages, aiming to make advanced language technology more inclusive and accessible. So thank you, sir. Now session is yours. I have already made you the co-host, so you can share the screen. Yes, your screen is visible. Now you can
Yeah.
start.
Thanks, Aditya, sir. Thanks for the warm welcome. And we'll start. My screen is not visible, right? Okay, we'll share.
Now not visible.
I'll
It
share
was
this.
visible now. You can reshare it again.
I will.
Yes, it's visible now.
Full screen. No, full screen is visible, right?
Yes, yes, full screen.
Okay. So, good morning, good day, everyone. So the session is about low resource machine translation via LLMs. Yeah, let's start. So machine translation is a subfield of NLP, natural language processing, or specifically natural language generation, where we automatically translate a source language text into target language. So it can be text, it can be speech as well, because speech is also a natural language. So the focus is on text. Let's understand a little bit history about machine translation. Then we will go along with the flow and move to more contemporary topics like using LLM for machine translation. So prior to 2000, basically it was mostly rule-based NLP, where for each language, uh, researchers or even everyone, whoever wanted to build a machine translation system, used to write rules. These rules are nothing but linguistic rules, where you write the syntax and specific examples, the all the rules like at minute details. Like for example, how we change it to continuous form, like eat and eating. Everything was being encoded as a rule, and that was how machine translation started. And tracing back to maybe 100 years back, or more than 50 years back. So this started when during the war between USA and USSR or Russia, where Russia used to have its own language like Russian, and the soldiers from USA need to encrypt or understand that. So they didn't know English, or they didn't know Russian. Sorry. So the rules or this a system was built which can translate from Russian to English, and this continued until 1990s also. Mostly more and more rules. So the next, somewhere around mid 2000, statistical machine translation came, where you provide instead of rules, the system was learning from data, like how we say machine learning. So given a set of languages and its corresponding translation or bilingual text, the statistical machine translation models used to learn the pattern, the common phrases based on the frequency, co-occurrence, the everything related to how the probability, like co-occurrence of each word, each phrase, and with a lot of data, So it is to learn the phrase table and that model, empty model. So that was the era of statistical machine translation. This statistical machine translation solved one problem. We need not to hand code all the rules of that particular language. How we used to do in rule-based machine translation. So now you have good amount of data for a particular language. You provide it to the model. Model learns and creates a like uh, model which can be used while inferring. That was statistical machine translation. But that was to be like optimized in phases. One is like building, one was the language model part in translation where you generate the target language. For example, if you're translating from English to Hindi, there are two components. One was the phrase table or the learning the co-occurrence between both the languages, creating a phrase table. So that was one part module. The second part was the language model, or which generates your language or text in second language. So there are two systems working in statistical machine translation. Then somewhere around 2010, neural machine translation came, and that revolutionized the complete machine translation field. So the improvements was huge. The accuracy which was seen in statistical machine translation and which was seen in neural machine translation was huge. Like we can say neural machine translation made it accessible and close to human level accuracy. So this neural machine translation came with once we with sequence to sequence models, encoder decoder based models. When we got attention available, attention module available to use. So basically, some we attend to different parts of the sentence, and the model learns the co-occurrence. So that was neural MT. So that even that started somewhere around 2014 with attention. Then it became like it again got a real boost somewhere around 2017 with the Transformers paper, which was like attention is all you need. So there the concept of self attention and all improved the accuracy of machine translation by again like plus 5 to plus 10%, somewhere plus 15%. So that continued until 2020s. And now also neural machine translation models are quite capable, but they are data hungry. They need data. Then from 2020s, the LLM-MT came into picture where we can use a large language model for the purpose of machine translation by instruction, following instruction, or asking through prompts only. Coming to neural machine translation, which is still prevalent and it is good for some specifically low resource languages, or where the large language model doesn't cover that language or the underrepresented languages, and if you have some bilingual or multilingual data to train. So neural machine translation, this processes the entire sentence simultaneously. It captures the broader context. Like that's what was brought in by self attention, and it produces output which is fluid and natural as compared to statistical machine translation or rule-based machine translation. Underlying this, there is a neural network, obviously. And here, what happens is like the process remains same as how we do with all any other natural language processing NLP task. You get the words or the sentence, then that gets converted to numerical representation, which is nothing but embeddings. And these embeddings capture the meaning in the like meaning in the spatial representation. And then we have the model, which is transformer architecture transform model, which is an encoder decoder model with attention mechanism. So this model learns, takes a source and target, and it learns how they are being translated, how to self attend to some other item, and this is how the model learns. Then once the model is ready, for the output, we once we pass the source sentence, it predicts the translated text. This has been for around 10, 12 years, neural NMT models. So all the major ones, the publicly available, for example, Google Translate, which many of us or all of us would be using sometimes, or even Bing Translate or Microsoft Translate or any other translator, the commercially successful ones were built on this neural machine translation. But now the paradigm is shifting. We either use sometimes neural machine translation models or use LLMs, depending upon accuracy and need. Coming to next slide. So large language models are again massive neural networks which also work on transform architecture with self-attention. But majority of the large language models are decoder only. But neural NMT models used to be earlier or now also they are more focused on the encoder decoder architecture. So that is a small difference. But large language models can also be encoder decoder. It can be of different combinations, but the majority of them are decoder only models. So the benefit of large language models comes with these are not specialized to NMT. So the same model can perform other NLP tasks like summarizing or even anything like even classifying, find information retrieval, and the same model can be used for machine translation. So we can rely on one model performing multiple tasks. So there is computational infrastructure, all this, even training multiple models has got its own challenges, which gets resolved using LLM. And usage is just by prompting, and we need not to train, and fine tuning is a different aspect where we'll discuss later. But through prompting, through simple instructions, we can get the job done. But the challenges now, let's come like that was a brief about history and how NMT used to work, and just touching around with LLM, what are they, how different are they. So challenges of low resource NMT was data scarcity. So the models which we talked, neural NMT models are machine translation models. So to learn that, they are really data hungry. So we need uh, at least 50,000, or maybe 50,000 is also less, somewhere around 1 lakh parallel sentences, for example, source and target, to train a decent model. So definitely a text and its translation is required. And the translation data scarcity is always a problem with low resource languages, which still remains like to build NMT. For high resource languages like European languages or even Asian languages like Chinese, Japanese, there is like we have a lot of data, so that's not a problem. But for low resource languages, data scarcity is a major bottleneck. And for coming to multilingual models are a type of neural machine translation models where your single model can translate between m cross n, like many to many. So for example, the same model is trained with English to German, French. It can translate from English to German, English to French, and the vice versa as well. So for example, it can translate from German to English as well as French to English. Basically m cross n, all combination. So there, due to transfer learning, because some languages may be similar, so sharing the multilingual space, they try to learn from other related languages. But one more issue, which is weak representation learning. So because of less amount of ratio or the less proportion of data in that multilingual training data set, the specific morphology or the syntax of the low resource languages is not well represented. Because for example, for English to German, we have 2 lakhs of data. But for English to Odia, we have, just giving some numbers, we have 50,000 or maybe less, 30,000. So one language pair is like 2 lakhs, which is like 200,000, and the other one is 30,000, which is like 6 times less than the English to German. So that ratio alters, and that's how the model doesn't see a lot of. If the model is seeing one time English to Odia, it is seeing 6 times English to German. So pair or while learning. So that increases the representation of that German. So the next challenge is domain sensitivity. As the data is already scarce, so how do we get for all domains? like for healthcare, for legal, healthcare uses its own terminology or the style of writing style as well as the terms. Similarly, legal domain also shows similar behavior. So you for low resource language data, generic data or the normal general use data is scarce. So how to get specific, that still remains a challenge. So the translation may be good at generic or domain, but when we move to a specialized domain like healthcare, legal, it further drops or it's worsens a lot. Then one more challenge is cross-lingual interference. So data is scarce, so we cannot train a one-to-one or a single model for that particular translation direction, like English to maybe Assamese or just taking some language, so any language or any some African language. So we need to train multilingually, where we mix multiple languages and train. There's still the, as we discussed, the ratio is high of the availability is high for high resource languages, so they still dominate. Um there is like you cannot increase a lot because some unrelated languages, for example, Russian and Hindi. Russian is a high ratio language, but they use the separate or complete different script, also the grammar. So that way, it will impact the low resource language, which is completely different. So thing happens. Then comes vocabulary person. So this vocabulary is the unique words, be it subwords or complete words, which which are used to generate or predict. When the model predicts during the inference stage, while giving the output, it basically gives one output at particular decode step. So if the word or a particular term was never in the training data, then it is the model has never learned that particular word during the training phase. So that is called as, that comes as a phenomenon which we see in while translating or generating the output. That is OV, which is out of vocabulary. If the model has never seen, it will never predict that. So if a particular word is missed from its knowledge, then that word will not be predicted. So ultimately, the translation will be less fluent and it will not be adequate. Adequate is, are we able to convey the same message in source to that when we're translating the translated text? So if the word is missing, it will never be adequate. That term concept can never be understood. Then comes orthography variability. Each language family uses their own writing, like basically writing system. So this script variability is also seen with low resource languages because as the script is not same, so it comes as additional challenge because they would never be sharing the same characters. So that particular script or that language needs to be learned isolated, because we our subword or a vocabulary learned from maybe a Hindi or a Devanagari script cannot be used when we are translating to something like Gujarati or maybe Telugu. So and the ratio varies in the training data. So this again adds on the to the challenges of low resource language. The main is the data scarcity. Everything else is related to that. As the data is scarce, so vocabulary is not learned, all vocabulary. The ratio becomes different in multilingual training, so cross-lingual interference comes, even weak representation learning comes. Data is scarce, so we do not represent all domains, so domain sensitivity is there. And that was, and now let's see, that was the challenges seen for building NMT models, and this challenges still exist for building LLMs, because LLMs still are trained with few popular languages or high resource languages, but with some representation of low resource. Let's look at the benefits of LLM based MT. So one is reduced data dependency. So LLMs are trained with large number of like trillions of tokens. They are LLMs because one is their number of parameters is huge, which is in turn relates to number of layers, number of all those things. And also they are large because they're trained on the web scale data, which is like large number of tokens. They are trained on monolingual data and also trained on multilingual data. This helps get understand that language. Also, it understands or captures a lot of knowledge about culture, about specific things. Because this reduced data dependency comes this way: to build an empty model, we definitely need parallel text. For example, if a sentence is in English, we need corresponding text in Santali or Odia or Bengali. But that is not always the case with LLM. LLM, we can send only English, only Russian, everything together, multilingual, but not in a parallel way. So that way we can train with more data, reduce data dependency. And stronger representation is because we are training with more data. For example, we may not be having just some numbers. So we may be having parallel data, which is English and Odia, the translated pairs for 50,000. Or let's take another language, English to Santali. So we may be having 50,000 data, but when we look at only English, we have trillions of records. Or if we take Santali, it has never 50,000. It would be definitely only Santali will be much more, like maybe 5 lakhs or 4 lakhs, something around that. So that was also a problem, like how to use monolingual. Monolingual data was being used for NMT, for pseudo translation or back translation, all these purposes, but it was not it didn't yield a lot. Like it was improving, but not a lot. But that those monolingual data can be used efficiently in while training LLMs. Then comes improved domain robustness, because we now do not need parallel text, so we can train it on multiple domain data. And same happens with better cross-lingual, because the data has increased. Even though parallel data is not required, with lot more data, it has learned this cross-lingual. It yields better cross-lingual transfer. So, and like in the last slide, we saw about out of vocabulary tokens, or some words were not being seen during training, or those are rare words, or even the frequency of those words were very less. So the model didn't learn. This gets handled better with LLMs, because LLMs do not need the parallel data. Then flexible adapt. This is a phenomenon or usage of LLM which improved its mass utilization and the usability. One is just by prompting we can interact with that, and prompt can be tweaked, changed, tuned, everything. And in context learning is about, you can provide some examples of translation, like you said, in the prompt itself, and it understands your style of writing and accordingly generates the translation. For example, we provide few examples where we say that we need a formal translation, in not in an informal way. So and we provide some examples, then the model follows the same pattern and translates in a formal tone. And there are other adaptation techniques like which change the model, like parameter efficient fine tuning, where you can train or fine tune basically, or improve the LLM to be more better in that particular task, or follow the instruction better, or provide extra additional training examples which are more domain specific or proprietary, something like that, which we think that the model would have not seen, not publicly available, so we can fine tune it with our own data and further improve it. These were some of the challenges which LLM like helped us resolve or mitigate, but still we have few challenges which are underrepresented languages. The most of the common LLMs are open source, or even the proprietary one to some extent are fine, but the most of the open source ones are still poor in extremely low resource languages or even underrepresented languages. The tribal languages are anything like beyond for Indic languages also beyond the 22 scheduled or official languages of India. There are many other languages which are underrepresented in LLMs and in NLP research. So that the challenges for those languages still remains. And LLMs are trained on huge amount of data, and they are with huge amount of data. Some they try to hallucinate more. That comes even if a word is less probable, they still generate a output or a translation which looks fluent but may not be correct. It is just a hallucinated text. And the biasness towards high resource languages still is valid because the knowledge which the LLM has learned or acquired is mostly from the high resource languages. So that whatever the learning from high resource languages gets translated or conveyed when translating to a low resource languages also forcibly. So now let's restrict the session to only open source LLMs which are free to use and do not cost like us anything other than the infrastructure to host or use it. But the proprietary ones are the closest one like GPT, Clouds. These models are quite powerful because they are in the range of 10x bigger the size and to some extent a lot more training data. So they are massive models. So their accuracy may be at a different level, close to human level accuracy for some NLP tasks, including machine translation. But the challenges which we saw, like underrepresentation, is still there for the paid LLMs or the closed source LLMs. Coming to open source, the popular LLMs which are good performing and have got decent accuracy in machine translation for Indic languages or low resource languages, including African languages and other low resource languages, are Gemma. Gemma is a family of model from Google, and Llama. Llama is also same family of models from family of models means it gets subsequent upgrades in terms of model or architecture improvements. Also, they have different versions. For example, 8 billion parameter, 12 billion, 3 billion, whatever. So different variants. So Llama is from Meta and Quen is from Alibaba. And these three models are seen, we have seen in literature as well as empirically validated. They are good with low resource languages. There are many other generic LLMs, but they are predominantly into English. One interesting thing is when we say they are good with low resource language, it doesn't mean that they're trained with lot of non-English data. Overall statistics says or the literature says these models are still trained with around 90% English text and 10% is for all other languages of the world. And there are some models which are specialized for translation. One of them is Translate Gemma, which is from again from Google. Like it's a fine-tuned version of Gemma. This is specifically fine-tuned for translation purpose. Trained on multiple languages using supervised fine-tuning, also reinforcement learning. So we can clearly see this a specialized. Similarly, Sarvam like has got models for LLMs which are good at our Indian languages, and they also have a variant called Sarvam Translate, which supports all our 22 Indian languages, and that is again a fine-tuned version of Gemma 3. This is developed by Sarvam and AI Farvara collaboratively. So next comes how do we use them? use this open source LLMs for translation. So prompting is the natural way of sending instruction to LLM. So the zero shot prompting is how we provide a direct instructions without providing any examples. So the instructions are the LLM performs the action based on its pre-trained knowledge. So one example is we ask it or send a prompt, translate the following English sentence to Hindi. The quick brown fox jumps over the lazy dog, and the model will provide output in Hindi. So this is zero shot prompting. This works out of the box. Like we can use it with any model, and we can change the instruction. If, for example, we want to translate from Hindi to X, then we say that translate the following Hindi sentence to English. And coming to another prompting technique, which is few shot learning. Few shot learning is we are giving the model few examples. Few examples, it has been seen that it can be two, it can be five. It can be two shot learning or three shot learning or five, anything. So these examples helps the model better understand the task and the expected output, so that it steers the model towards that specific learning or the specific style and specific task requirement. Here we can see one example. For example, the input was we are providing it three examples, which can be said as three shots. So one input is hello, how are you, and the output is namaste, aap kaise hain. Similarly, we have other examples. Then we ask it like new input is welcome to our home, and the model will translate it. Here it learns from the examples. We definitely also need to provide the translate the following English sentence to Hindi as a like opening statement. This is how we interact with LLMs for translation. Yeah. So now we will move to looking some like hands-on how to use them and how to tune the prompt and all those aspects. Before that, any questions until now? We can take questions for like 5 minutes or 10 minutes.
Yes, any questions? You can unmute yourself. That's the question. Anyone? Bala? Subhasri? Any question from your side? Yes.
Hello, yes, sir. Am I audible?
Yes,
Yes.
yes, audible.
Yes, sir. As you told one slide, vocabulary will use during inference, right?
Vocabulary is? Can you come again?
Vocabulary will use during inference.
During training, it learns the vocabulary
Okay.
from the training
So,
data.
like how it will learns during training, like how miss there is some miss maybe create the vocabulary mapping something, right?
Correct.
So
So,
how it will done? Like suppose just example, you take Indian to Indian language or any language,
Mhm.
English to Odia. So some language don't know Odia. Some pretend model, sorry. Some pretend model doesn't know Odia. That is based on only that train on based on the other languages, other high resource language. So
Correct.
how that model understand? How build the vocabulary? That I wanted to know.
No, if it is not there in the pre-trained like training data set, it is really difficult to make the model learn a new language. So the
So
point which I brought in was for training neural machine translation model, or while you are training a small LLM like SLM. So in that, if your training data doesn't has that language, it will never learn. So it will always throw some hallucinated text because it has never seen Odia, so it will never learn the vocabulary.
So
What?
means before do any translation, we need to choose the model which already know that
Correct.
language. Is it like that?
Yes, we'll have to test it empirically. So that's why I said generic one. Because if you see, these are not the only one famous, right? We have Mistral, we have many other. We have five, we have many other generic LLMs. These are the ones which I have tried at least they know our Indian major Indian languages because there are n number of languages. Some LLMs are trained for only African languages. Some are trained only for Indonesian language or even European languages. So those we cannot take it for translation of Indic language.
So how will
We'll have
tackle?
to read.
So how
Yeah,
will miss? I don't think most of the models are which train on the Indian languages. Very few models, right?
correct.
So how will miss do the task like for Indian languages?
Yeah, so all of this, Gemma is trained, Llama is trained, Quen is also definitely trained, Sarvam is trained. So we can pick one of them.
Okay.
Or if you want to go for closed source models, GPT is perfect. GPT is perfect. Cloud is perfect. All these models are already trained on Indic languages.
Okay. Okay. Thank you.
Thank you.
Sir,
Yes, sir.
hello, sir.
Yes,
Welcome.
Anwar.
Hi.
Sir,
Sir,
I
can
am
I?
asking that in LLM training in low resource machine translation. So we are using your data. We are not giving data parallelly. We are for processing. We are giving everything as a whole, monolingual or multilingual text. So, sir, what I am asking that when we are doing in context learning, shouldn't we use parallel processing as we can see from the both side of a sentence from the starting and the ending end, like like Bert uses it. So why are we not using uh,
Parallel data you're
parallel
saying, right?
processing? Yeah.
Yeah. So these LLMs are not specifically built for machine translation, right? So they are basically language generators. So they generate like in a so they are they are made. We have never seen the how the exact data how this open source models are trained. In they will be having monolingual. They also may be having some representation of multilingual or parallel data. Sorry. But the ones which you see on the screen, Translate Gemma, Sarvam Translate, they are definitely fine-tuned on parallel data so that they see the source under translate text. That's why these are specialized translation ones. These are specialized translation LLM because they have seen the parallel data, both the sides.
Okay, sir.
Did I answer your question?
Yes, sir.
Yeah, sir. One question I have, maybe very basic questions.
That's fine.
Sir, like you means like parallel data set. I'm talking about the data set. So
Yeah.
in parallel data set, suppose let me talk English to Hindi. How are you? आप कैसे हैं, right? So means what is the suppose I want to create the data set. So what I think like minimum tokens in the source sentence or target sentence that I want to know. Is it
Minimum number
single?
of tokens.
Yes, yeah,
So that
minimum number.
is fine. Then that is fine, but we should have a good mix of like this distribution. Some short sentences, some like medium sentences, some long sentences. So that way the model learns the variability as well as model learns the dependency, long range dependency. For example, if here it is just three words, how are you or something.
Yes,
When,
yes.
when we use a phrase where a comma is there and a depending phrase is there, for example, a 15 words and then there will be text somewhere or a word, sorry, word somewhere at the ninth position, which is depending upon the second position word.
Okay, fine. Can we take the single word also?
Single word they will not learn the grammar. We can take, I'm saying you can always add this. See, when you are really have something to be used that way, one word like
Means
what is
why I'm asking because maybe impact on the performance. That's why it will be good for machine translation output performance or will we decrease something if you have done some hands-on experiment, whatever,
yeah, but when we
according
are
to your
saying
experience.
one word, you want to train only on a parallel training data set which has got single word like a dictionary.
Yeah, yeah.
No, that will not. There will no learning. It will be just translation like text by text.
Mhm.
How someone will. It will not learn the grammar or it will not even learn the syntax of the language.
Why I'm asking, sir? Because some of the language like Sanskrit to Hindi, suppose Sanskrit to
Hmm.
any language we want to translate and having the some big words, right?
Yeah. Mhm.
So maybe that is the impact of the single word also to do the data set create like that.
Data set, training data set is different, but the single sentences, if you these are important ones or a validated one, then this can be passed for your fine tuning, or it can be passed while in your prompts also, like some examples. How we see here examples, right? So here you can provide some real sentences so that it can it will know how is it, like basically it will understand that we need to translate in this particular way. So here how I provided some examples, right? Then you can provide those single sentences if they are really critical for that domain or for translation.
No, just I want to know
But for
suggestion like, sir, just I want to know suggestions like, is it give the benefits or we have to
it
ignore
will
that?
give benefits. It will give
Okay,
benefits.
okay, okay,
For
thank you.
example, for I'm giving an example. For example, a model LLM is trained to say, just a hypothetical example, to always say instead of Odia, Oria. Okay, how we used to write it earlier before it was renamed ORIYA. But
Yeah,
now it is official that we use ODIA. This information you can pass as a single word, then it will learn. Okay.
okay,
In the prompt, these small things which are really relevant can be passed as a single word. So the next time model will know. Even the model's training data has got Oria or like the literal one. So then, but if you pass it as a in your prompt that it should be called Odia, ODIA, even if in writing in English, then it will learn it and it will accordingly generate.
okay, sir. Thank you, sir.
So this definitely helps.
Okay, thank you, sir.
Thank you.
So quickly take questions.
Yes,
Anyone? Rupesh or Basir?
yes,
Any question?
yes, sir. Yes, sir. I just want to ask, sir, like one of the problems of the LLMs, like the hallucination.
Yeah.
So, like, how can it be detected at the point of the translation when you are using the LLM to make the translation? Like, how can we, detect the hallucination, and how possibly can we, resolve the issue of hallucination?
Got it. So one thing is detecting hallucination is an active area of research. It is really tricky because it will look so fluent that many will miss that. So hallucination is detected only when evaluating the model, when you have a reference or the ground truth, and when we compare, we see that it is completely irrelevant. When we are calculating a relevancy score or how good is the translation or how much information is captured, then we come to know that it is completely irrelevant. But when you are really using it, there is a real chance or the high chance that the model has hallucinated and we do not know also if you are not really observing it. And to reduce hallucination, one of the way is this fine tuning, like to provide it your own data. Like that PEFT. PEFT is nothing but parameter efficient fine tuning. When you provide it more domain specific data or the data which is different or which you think that this data is not publicly available, so the model would have never seen our data, so we should train or fine tune it on our data so that it learns and it doesn't hallucinate. It definitely, it actually we should when we understand it hallucinates when it is not confident what to answer, or when few two concepts are close enough that it is difficult for it to confidently decide what should be the output. In that cases, it hallucinates. Like even if it is less probable, it knows, still it generates something which looks really fluent. So one thing is we need to fine tune it with our own data. The second is instructions, like prompting techniques, like different prompting techniques are there, right? Like for example, chain of thoughts. When you ask it to reason and react, we can say it to consistently. Once we generate the translation or the generated output, we ask the model to internally verify, like as a second step, so that it tries to self consistency check. In that process, when it finds some inconsistency, it changes its own generation of the output. So one is that following different prompt techniques, like chain of thoughts or even react prompting, all these things. And the other way is showing it or providing it the real knowledge so that it doesn't hallucinate through fine tuning. Did I answer?
Yes, sir. Yes, sir. Thank you, sir.
Okay, so quickly last question from Rupesh, then we'll go for the demo. Yes, Rupesh.
Hello, am I audible?
Yes.
Okay, good morning from Nepal. Just we talked about the out of vocabulary problem, but if we use the tokenization techniques using byte pair encoding, I think there will not be any out of vocabulary for any low resource language. Just the problem will be token fertility. So can this be the solution for low resource language, or we need to work more to find the solution?
We should work. This is a solution which came with BP and subword tokenization, like maybe some 8 to 9 years or 10 years back. So, but these subword also has got its own limitations. So, what happens is subword limit tokenization or the byte pair encoding or Enneagram, they reduce this out of vocabulary thing, but doesn't mean that if a language at all is very well not well represented and it follows a completely different script, then it still happens that it generates a translation in a different language. I'm giving an example, like one of my works. So when we try to translate using that model from English to Odia, it generated only or 90% of the time in Bengali and Gujarati mixed script. So it also depends upon the representation. But for NMT training models, this resolved because there were limited number of languages we used to train, and that was sufficient with subword tokenization to remove this out of word vocabulary. But when coming to underrepresented language and using LLMs, this cross-lingual interference is still there. Is this clear? Did I answer you?
Yeah, thank you.
Okay, then we'll go for the demo.
Sure. My screen should be visible.
Yes, visible.
Okay. Okay. Let it connect. Okay. So to use a open source LLM, the default or the de facto location is to get a model if it is available in Hugging Face, and to use the Hugging Face ecosystem, that is Transformers Python library, to use it. So we'll follow the same approach, and everyone these days is following the same approach. And as we all know, we need a GPU enabled machine or a notebook where we can use it. And here we are using a GPU L4, which has got 22.5 GB of RAM. Some models, some 4 billion models, or smaller ones, can be done with 16 GB or less also, or 12 GB. But I have taken this so that we do not get out of memory or some other errors. Okay, so for this we did this, and we definitely import this way, like transformers. From transformers we need this causal LLM module. Also we need the auto tokenizer and the auto processor. Also auto processor and auto tokenizer process our input and output text, and auto is because it can be used for different models which have their own tokenizer, but the module automatically provides the relevant one. Same this This is a generator, like image text. So these are different modules available inside Transformer. We import all of them, which we'll be using. Okay. So now let's start with this, which is Gemma 4. E4B, this is a model which was released this year only, Gemma 4 family of models. And E4B is somewhere around 8 billion parameter model. We use this is how it is in Hugging Face, like Gemma 4 EB, IT is instruction tune. And we load the model like from pre-trained. We provide the model name and it loads. The processor gets loaded in processor and the model is loaded into the model from pre-trained, because these are pre-trained models. And the type is nothing but what is the data type, like B float or float. This we can keep it as auto, so that it maps to the available hardware as well as the model trend types. And device map is auto, but it is basically, it says that where to load the model in CUDA. Usually it is, because we are using GPU and we need it. When we run this, it pulls the relevant files, chart template, model files, set sensors, all those things, and even the tokenizer. This is being pulled from Hugging Face. In the meantime, we can go through this. Yeah. So there can be different prompt styles. One is just we say that there is a system prompt, which is remains the constant for that particular conversation. System prompt can be like translate from English to Hindi, and in user we just provided the source sentence. Run that. No. Yeah, models are still getting loaded. Yeah, model is loaded. So here what we do is for us, the source sentence, I have taken a simple one already initialized in the above. Bhubaneswar is the capital of Odisha. This there can be different prompting styles where we see here system can be provided a system prompt, system message, then system can also be empty, and also ideally we should say what is the role it is playing as a system. So you are a translator, translate from English to Hindi, and these are the different variants which we call it like prompt tuning. With this we can achieve a lot also. Prompts really matter. And just analogy, there is a recent paper which is saying that if you provide the same instruction twice, just a repetition, that also improved the accuracy on the output. There was a recent paper this year only. So prompt tuning still has got scope, and some people have started calling prompt tuning or writing efficient prompts is also a science. So now let's say, like it is just in text was that, and this inputs basically has encoded it, and our text was here like source en. Then we got a message where we give the roles assistant, sorry, user and system, and that got converted into its like numbers. So this is how the inputs get converted. Then what we are doing is model or generated. Model is the GMA4 model which sits in this particular object. Then we have this generate and we say that how many tokens to generate. 1024 is sufficient for generating a single sentence translation, or even 512 is also sufficient, but we can change it. So, and the response. So basically when the model generated some text, what we see is again model also generates in numbers. Then this response, what it did is it just converted basically decoded using the tokenizer and response we got. Then we have a processor which converts it back to the natural language text. So if you see this, here we had some special tokens, and all these special tokens are end of s, end of string, end of sentence. These markers are post processed using this processor. All these processors are defined over here. So these are basically, we use the auto processor module from the transformers library and we give it the model ID, which is nothing but the model name, and the relevant processor is loaded for that particular model. When we pass it to the processor, it gives us the translated text, like Bhubaneswar Odisha ki Rajdhani hai. This is Hindi. Similar, and this model is a 8 billion model which takes around 15 GB of GPU memory. So anything below 16 will not be sufficient, and we cannot infer using this. At this precision, we can definitely quantize or load a different version of this model to put in. Again, the accuracy drops slightly. So with the vanilla model, for this particular model, we need around 16 GB. And yes, and coming to different styles, let's see someone doesn't provide a system prompt and it says translate from English to Hindi. We are using the same source sentence, the same text, but we do not use a system prompt. So in that case, we didn't explicitly use a system text, so it provided output, but it in the previous one it just gave us a translation. But now when we use this particular one where the system prompt is empty, we see a lot of generation, like it tried to explain itself. Let me copy it. So it is basically saying the responses here are a few ways to translate Bhubaneswar into Hindi depending on the desired formality. So most common, it tries to explain itself with a lot of generation. So here it provides in the Devanagari script, then it also translates in English or Latin scripts, and then it also provides a slightly formal, most common, then it tries to generate a lot. So it keeps generating until either it reaches the max number of tokens or it predicts that that is all, like end of sequence. So that's why this here. Max new tokens is required sometimes. So when you are not providing a system prompt, it converts as it is, like however it wants. Like with rational formal translation, it becomes a conversation then. Then now when you are saying that you are a translator, translate from English to Hindi, then now we are using this prompt style, and we do this, then we copy this. We'll see. Yeah. So here you can see this. Here also similar. Here are a few ways to translate Bhubaneswar as the capital of Odisha. Almost similar. So there comes the prompt. Let's use this. Then we get that way we get the output like Bhubaneswar Odisha ki Rajdhani hai. And look at this output and the more conventional style, like everything, like whatever it thinks and formatted, and so these everything depends upon how well we do a prompt. Similarly, we can see it's okay. Okay. Similarly, when we look at few shot prompting technique, there we can say a system prompt is like you are a helpful assistant that translate English to Odia, only return the translated text. So the instruction is clear, and then the content is this part which I have highlighted is basically a one shot or an example. Kolkata is the capital of West Bengal. Then we are giving it a text to translate. The source EN is the same one, like basically the Bhubaneswar is the capital of Odisha. So now let's use this message, which is an example of few shot. Then what we do is we process that text like or the message. Then we see, if you see the input length also, it would have, that was 29. And now if you see, it is 89. So because the one extra example went into. So number of tokens is fine. Then now we are generating the output. Now let's see the output from this one shot example. So that was, we instructed Odia, so it was generated in Odia. Always the few shot example is not required. We can start with zero shot, then add like few shot examples. The ideally we can start with one or two example and go up to three. So some people have tried with 5 shot example, but that again increases the input token and latency and other things. But 2 or 3 should be a good to start. 2 examples. And in the same language makes it much better. So for example, we wanted to translate from English to Odia, so we will restrict the example also to be in source as English and the translation as Odia. So this is how we translate using zero shot and few shot technique, the Gemma, like or the generic one, Gemma phone. Now let's look at its variant. This translate Gemma is a translation specific LLM, which is fine-tuned version of Gemma 3. Here, let me start session. Now we'll see a specific model, which is, I'm just restarting the session. So there we show how to prompt a generic LLM. Now we will see how to use a translation specific LLM. What we do is, similarly we do this. It will it will import the libraries, modules, and then this is fine. Then what we do is, the GPU memory is already cleared. And this translate Gemma has got different versions. Like one is 4 billion, they have something 12 billion, 27 billion also. Definitely, they have their system description paper or the paper available. So if required, how they have fine tuned, they've taken the Gemma 3 and they have fine tuned it on parallel sentences, also on the real phone spent learning how to which is a good translation, just basically providing reward for a good translation and penalizing for when the translation is bad by the output, so that it learns through this reward and penalty RL structure. So we are using here translate Gemma 4 billion. That should take somewhere around 8 GB of GPU, so decent enough to load on any GPU. Let it load. And here this follows. Here the best part with specific or the task specific LLM is the impact of choosing a good prompt or an instruction, like how we said in translate without generating any extra explanation, or you are a helpful assistant, translator, or the system prompt are already handled during its supervised fine tuning. They took the Gemma 3 pre-trained model, they fine-tuned it for translation purpose, and they provided all these instructions during the supervised fine tuning. So that way we need not to pass anything like instruction what we need, because this can do translations only. So the message looks simple. We are a user and we are translating text and translating from English to Odia, and we are providing the source text. And if we look at this, it takes around 8.2. So around that much GPU is minimum required just to load a 4 GB model. Then we are processing it. Inputs gets processed, and here we are generating the model output. The model is called and it generates. It is a 4 billion model, so it was fast as compared to the 8 billion one. So now we are decoding it, and then when we give an output, it says Bhubaneswar Odisha Sahara Atte. But when we look at this was our last output with the few shot. So this says Bhubaneswar Odisha Rajdhani, and the translate Gemma says Bhubaneswar Odisha Sahara Atte. But if you see the source EN, it is Bhubaneswar is the capital. We do not see the Rajdhani. So this is how the impact, or we can see a real example of low resourceness of Odia. Translate Gemma, they claim that it is much better. It is much better, but for high resource languages, definitely it is better. European languages and many other. It can translate Odia, doesn't mean that it will convey all the information. For example, it completely missed the Rajdhani word, which is like for non Odia speaking attendees, like it is equivalent of capital or a translation. So we do not see the capital being represented. So this was one example when corporates or research organizations or universities are releasing, but we need to have our focus with low resource and our languages. there is still a lot of work to be done. So this was how we infer or use a translation one. Similarly, we can do it is very similar. Like there is Sarvam Translate from our own Sarvam AI Indian company, and Sarvam Translate supports all 22. Here also similarly, we provide a small instruction, translate the text below, and we provide the target language and the parameters, and it translates. And we similar way, like we then get the model output, we process it or tokenize it, then we give it to the model for prediction, then decode the predicted prediction, and we get the output. So here with the same example, it was able to capture the Rajdhani word, Sarvam Translate, because this Sarvam Translate has seen only our Indic languages. It is focused on Indic. Even though the base model is Gemma 3, but they have fine-tuned it. But the Translate Gemma, which we saw, missed the Rajdhani word, is trained on, I don't remember the exact number of languages, but all the major languages. So that way, this is underrepresentation. The data which would have gone for Odia is much less than others. So it lost that capital is equivalent to Rajdhani. That translation got missed. So here it gives just a city like Sahara. Yeah, this was a demo. Like any questions on this? Free to take the questions.
Yes, any questions from the audience? Just raise your hand and one by one ask the question. Yes, Subhasri, you have some questions you can ask first. Hello? Yes. You are not audible. Subhasri, you are not audible. Anyone else? Have you got everything or what? No questions.
Yeah, can you hear me? Can you hear me?
Yes, Bala.
Yeah, can you hear me?
Yes,
Oh,
Bala.
okay. I just wanted to ask more questions with regard to the long.
One by one.
Hello, can you hear me?
Yes, Arpa. Yes.
Okay. I wanted more clarifications on the long-range dependencies, considering that the n-gram language models only consider the previous n word. So I just wanted to know, how do they handle these long-range dependencies? How do they maintain the global coherency and understand the complex synthetic structure in the natural languages?
Yeah. So basically, long-range dependency is definitely better than NMT models. NMT models we used to train on couple of sentences or a single sentence or segment. But these LLMs have seen are trained in a different ways, and their input context window is much more. Like now, even if you see some models market with having 1 million context window, like the input context and the context. So that way they are able is better because they are trained in that way, and these are large models. So even their attention modules are stronger. So that helps in attending to long range dependency as compared to the NMT models. This comes because of in nutshell, because of the model architecture. The LLMs are large because their capability of understanding or capability to learn from the training data is much more. So they are able to attend to the long range information. Hope I answered.
Okay, Bala, you got?
Yeah. Yes, sir.
Okay. So, Orko, yes. Orko, you have some questions?
Yes. Thank you. So, good morning, everyone. Good morning. So, Amulya, I have a question. So, what I've understood is that each and every language belongs to a family of languages. So, there shouldn't be some sort of similarity within the languages which we can somehow utilize for LLM training and fine tuning. And if this like the entire the training task, if it is centered around phonetics, like the similarity of sounds, would it help to solve this low resource problem?
Yes. So basically, family of languages definitely help. This is why the translation performance of LLMs or multilingual NMT models for European languages is better than Indo-Asian or other, like Indo-Aryan and other language family, because the European languages also use the Latin script. So because of that overlaps belonging to the same family, so they are better. But here India is a diverse country, so the script which we use for Odia is not the same for which we use for Bengali. So that way they learn, but when we convert it to the generating in the actual script, it is tricky. So they are different. So that way they learn the, but the not the exact generation which we is really required. They learn the concepts at the embedding layer. Like when they that learning is fine, but when you're generating, you need to generate in the original script.
Okay.
Native script. So that causes similar family is fine. Similar family, yeah. For example, I had one paper where I was working on Hindi and Chhattisgarhi. So they both share the same script and they are very close enough. May not be dialect or maybe dialect, but they are similar, at least 80% or 90%. So that way, one language, when a model which is good at Hindi was also good at Chhattisgarhi. But this usually doesn't get transferred for other languages, where the writing script or the script is completely different.
Okay. Understood. Thank you, Amulya. Thank you.
Thank you, Akash. So, Subhasri, yes, you can.
Yeah. Now am I audible, sir?
Yes.
Yes.
Yeah. So hi, sir. Good morning. So my question is, sir, if we want to create an translator model or AI powered model for a low resource languages, like the script might be same with Odia, then what should be our approach? Like we need to go for the machine translation or the transformer. Like what should be the approach, and how much data we need for the model to to be a
Okay.
useful
So you
model?
want to build a fine.
Yes, Amulya, she is working on the Deshiya language, actually Koraput Deshiya language. So it's very difficult to collect the data. She had collected only, I think, 1,500 to 2,000 sentences like that. So, and she can also collect the words also. So how she will proceed? Means she need your suggestion how she will progress.
Yes.
And Deshiya follows our Odia script only, right?
Yes. The writing style is little bit different, like the her length and
Okay,
some
small
special.
ones, minor ones.
Yes. But yeah, as you said, 80% is similar only, like with the Odia.
So here you can take few of the examples and try to just use in context learning, which is by prompt or all those things, provide some, like how we saw in few short learning, right? So you can increase that to maybe 10 languages, 10 sentences, and see on any other LLM is able to translate at least one, like another sentence. Like, is 10 showing just 10 examples to the LLM enough for the LLM to learn and translate? You can do such experiments with prompts, because even with less data, thousand you said, right? There is definitely the NMT or the transformer one we cannot develop with
Okay.
such less. But you can develop a multilingual way where you have some examples from English to Odia and that part, and add this language that you can experiment. The second one is you can take few of the good examples from this year and pass it in the prompt only as few short learning and see that whether it is able to translate in this year instead of Odia. And in the instruction, let us say is Desya is a language spoken in Odisha and it is similar to Odia. some hint we should give. Then try that if the LLM can learn.
Yeah,
These
I
two
have.
will be the, yeah.
Yeah, yeah.
Go ahead.
I have tried with that using the LLM model, giving few short examples and tried that, but the
Okay.
accuracy is not coming perfectly because the script, it is not able to generate the halant words. So in place of that, only the zero or round is coming. So
Yeah,
that's
that is some challenges will be there.
yeah. So for the transformer part, how much data we need and how we can.
No, minimum 30 to 50,000
Okay, sentences you are saying?
sentences.
Okay, okay. If we
So
will collect 30,000 of data, then it is possible,
we
right?
can give it a try, but it will not be perfect or fluent.
Okay. But in NMT and translator model, we can achieve.
Yeah, transformer is same NMT only, right? So
Yes.
NMT in these days is being realized using transform models.
Yes,
But
transfer model you are thinking.
yeah, but 30 to 50,000 is the just to start. Then accuracy
Okay.
won't be that great, but at least we can see some results.
Yeah, after that also we can use reinforcement learning or federated learning for that to improve the accuracy.
But how do we get it? Yeah, we can try all these things. The first thing is data.
Yeah, okay.
So we can try, but
Minimum 30 to 50,
hmm,
then only you can see.
correct. Then we can look at next steps.
Okay. Okay, Amulya, that's it from my. Thank you so much.
So any other questions? I don't think so. Okay. Okay, then I don't think so there is any questions are there. So recording is going to be shared to all. Okay. If any queries are there, you can contact to me and we can contact. So I can contact to Amulya sir, or you can directly also contact. So thank you very much. Amulya sir, thank you very much.
Thank you, sir. Thank you everyone for attending.
Okay, so that is the end of the session. Thank you. Next
Thank you,
session.
everyone.
Thank you.